So the final thing we're going to look at is a Moran process on a game. So we're going to consider two types of individuals in our population. And we have a matrix A, and the first row will correspond to the utilities of the first type when they interact with an individual of the first type or of the second type. And similarly, the second row will be the utilities of interacting with the second type and the first type. So once we've done that, we're going to use these utilities to define our fitness. So a particular strategy is actually very good when it interacts with itself, and there's a population with a lot of individuals of that first type, then it should have a higher probability of being selected. Okay, so the way we do this is that we have all our individuals of a particular type. Let me use the same colors I've used there. And then we obtain the fitness for all of these, and we do that just by using this calculation. We'll talk a little bit more about that. And then to select an individual to reproduce, we use their fitness. So this is not just a uniform random selection. So it's not uniform random. It's not uniform random. It's a selection dependent on their fitness. So if you've got a high fitness, so if the reds, for example, had a higher fitness because there's more of them, so they're doing better because they're interacting more with individuals of the same type, then they're more likely to be picked for, oops, let me just stick with my colors, more likely to be picked for reproduction. So we pick one, we reproduce, and then we, however, do select for the death, we do that uniformly. So we just pick anyone for a death, and so in this particular one we happen to have picked something, an individual of the same type, and so we arrive at the same system that we had to start. Okay, so the main difference is that the way we select someone to reproduce depends on their fitness, and these fitnesses come out of the game. And we're gonna write down what those are. So we'll write down the fitness of an individual of the first type when there are I individuals of the first type. Well, they're going to get a I minus 1 of the time, right? So there's I minus 1 individuals of the first type, so those individuals will contribute A. The B will occur n minus I of the time, and we divide that by n minus 1. So this is in fact a probability, and actually it's a mean fitness across the population. So it's an average fitness where the probability of getting A is I minus 1 times n minus 1, because if the individuals of the first type, there are I minus 1 other individuals of the first type. And then similarly, there are n minus I individuals of the second type. And then we have F2I, so this is the fitness of the individuals of the second type. They get a C, this C here, they get a C I of the time, because if they're I individuals of the first type and they're of the second type, then they get their I of the first type. And they get a B, n minus I minus 1, and divide that by n minus 1. So these are our fitnesses. And then what we do is we calculate the probabilities of the states going up or down, just in the same way. So we have that pi I plus 1 is going to be equal to the probability that we select an individual of the first type to be reproduced. And we do this by weighting the probability by the fitness. So that's just going to be I times F1I divided by, and this is just to normalize, I F1I plus n minus I F2I. Right? So that's just selecting the individuals according to their fitness. Every individual of the first type has this fitness, every individual of the second type has this fitness, and so this is the total fitness, and this is the probability of selecting one of the first type. But as I mentioned, we remove members of our population in a uniformly random way. So if we're going to go up by an individual of the first type, we have to take an individual of the second type out. And there are n minus I of them, and we divide that by n. And then likewise, let me stick to my colors, pi I minus 1 is going to be n minus I times f2i, divided by the same thing, fi f1i plus n minus I f2i. And now, however, we multiply that by I over n, which is the uniform chance of selecting someone of the first type. But if you recall, we're not actually interested in this. The formula we have from the birth-death process, the general birth-death process, gives xi, the fixation probabilities, in terms of the ratio of pi I plus 1 divided by pi I minus 1. And we can just calculate that to be gamma I. And if we look at these two ratios, so it's pi I plus 1 divided by pi I minus 1. And if we look at these two ratios, we see a lot of things are going to cancel. Those are going to cancel. This n is going to cancel. This I and this I is going to cancel. And this n minus I and this n minus I is going to cancel. And so what we're left with is f1i divided by f2i. And so we can write down that using the theorem that xi, the probability of the first type becoming fixated if we have I individuals of the first type, is given by 1 plus sum j equals 1 to I minus 1 of the product from k equals 1 to j of f1i divided by f2i, divided by 1 plus sum j equals 1 to n minus 1 product from k equals 1 to j of f1i f2i. And that gives the general formula for the fixation probability of the individual of the first type. What we're going to be interested in a lot is the probability of a particular type of individual being able to resist invasion or indeed invade. So if we have so many individuals of the first type and we throw in one individual of the second type, the probability that that individual survives is what becomes interesting. And what we're going to be interested in is talking about row 1, which is if we throw one individual of the first type in, can they into a population of everyone else, can they be fixated? And so that's x1. And row 2, which is just the same thing for the second type, is 1 minus xn minus 1. And that's essentially Moran processes, and using these probabilistic methods to be able to see not only do individuals do well against other individuals, but what happens when those individuals have nothing but themselves to interact? Do they start to tear each other apart? And that's what we're going to be. Well, that's what we've looked at here.